Okay, so memory management. Just a quick review. We had talked about how when we have processes, the ultimate end to the compilation process is to come up with a load module. Okay, and these load modules have their own internal sense of what their memory representation is, right? So we call that the logical address space. Okay, so from the perspective of the process, the memory address that it has, the memory addresses that it has, begin at 0 and go up to m, or m minus 1, where m is the total number of addressable words, memory words, where words can be some number of bits long, usually 32 bits long, 4 bytes, that the process takes up. Okay. Now, unfortunately, this logical address space has to actually be loaded into the physical address space. And the physical address space is simply the total number of addresses in random access memory, in RAM. And it has an actual size of between 0 and n minus 1, where n is the total number of words in the entire RAM. Okay? So since we've got a bunch of these load modules, all of different sizes that are all competing, these are all running processes, they all have their own logical address space with different values of m. Okay, so every process gets to think that its memory starts at 0 and goes to m minus 1. We need to load these into this physical address space so that and what's in here, by the way? Well, what's in here are instructions, data, instructions that include functions. Okay, so references to functions are in there, data is in there, the stack is in there, the heap is in there, right? Various parts of information that we need for processing. Each of these individual processes is stored in this location. And by stack, I mean the function call stack. Okay? So when we load these in, we need to be careful because this is not going to be 0. Okay? This is going to be some value x between where x is greater than 0 and less than, greater than or equal to 0, and less than or equal to n minus 1. Okay? And x plus whatever the size was, where this value is greater than 0 and less than or equal to n minus 1. Okay? This one might go here in this space. Okay? This one might end up here in this space. This one, hold on, question marks abound about that one, because this one no longer has space to go in here. Okay? And the processor, Intel or AMD, whichever religious sect you belong to, okay? The processor only has access to RAM. It doesn't have access to the disk where we're storing the load modules when they're not in active memory, okay? So we have to figure out a way to swap something out to make room for this guy, okay? And one of the things that we talked about on last week, on Tuesday, was how do we do management? How do we do space management? Okay, to try and keep as little holes, right, as little fragmentation as possible, right? In fact, what we want is we want the largest holes possible. We don't want our holes to get We don't want our holes to get small, and we don't want to get a bunch of holes. We'd rather have fewer large holes, right? Because that allows us to put more modules in, modules of significant size. Tiny holes, they can't fit modules. Okay, so we talked about that. That is an example, right? So when we have that kind of fragmentation, we call that external fragmentation. Okay. All right, so that's all review so far. Have you guys got any questions about any of that? Incidentally, the basic act of making room for modules that we don't currently have room for is called swapping. Okay, and there are of course a lot of different approaches for how to affect swapping, but I'm not going to spend, and the book doesn't either, I'm not going to spend much time talking about swapping because it's just not a good solution. We want to move on to better possible solutions. Okay. Any questions before I go on? All right, so let's talk about some better possible solutions, right? Because our hope is that there is a better way to avoid dealing with external fragmentation. Okay, can we get rid of external fragmentation altogether, right? Let's talk instead about paging. Okay, there's this notion of paging. How big is that sheet of paper on the wall right there that tells you to wipe down your surfaces when you get here?
8.5 by 11.
Okay, 8.5 by 11. What size frame, if we were going to frame that piece of paper, what size frame would we need? Okay, 8.5 by 11, the same size as the paper, right? If you got a 5 by 6 picture, you need a 5 by 6 frame. Okay? So the metaphor that I'm about to explain to you is about framing things. Okay? So a page is a set chunk or size or piece of logical address space. Likewise, you've got the notion of a page size, okay? And page size is the specific size of all pages in our system. So all pages are the same size. Okay? All pages are the same size. So what we're going to be doing is we're going to be taking all these various address spaces. Okay, so I got an address space here, I got an address space here, I got an address space here, I got one here, and I'm going to be carving them up into page-sized chunks. Okay, and each one of them is going to be like page 1, page 2. Okay, page 1, page 2, maybe page 3. Just page 1. It only takes one page to store that. Okay, page 1, there's some left over, page 2. Okay, and so it's a fixed division, a fixed size division that we're going to be dividing all of these logical addresses up into. And now, why would we do that? What difference does that do? What does that do for us? Well, we swap. Okay, so a page is also the smallest chunk of memory to be managed. Okay, so a page is made up of some number of words, right? Each page gets picked up by its whole in its entirety, and it gets moved into RAM. And RAM is divided up into a series of page frames. Okay? This is a chunk of physical memory. And no points for guessing, page frames have page size. Yes. Oh, you can't see that. Thank you. Let me do this again, because physical memory is divided up into page frames, and each page frame has a page size. Okay? And any page frame, all the page frames, any page frame can contain any page, because they're all the same size, right? So what we've done is we have taken RAM, taken our idea of RAM, and instead of putting in chunks of various size modules, all I've done is I've said I'm going to divide this up into, some number of page frames. So this is page frame 1, and this is page frame 2, or just frame 1, frame 2, page frame 3. They're all the same size, page frame 4. Okay, and yeah, I've got all these load modules out here who are ready. These are entire processes who are ready to be loaded into the RAM, but they're also divided up into page frame chunks. Okay, so this is page 1, page 2. This is also page 1, page 2. This is also page 1, page 2. And when I get ready to load, let's say, this module, okay, I take this entire chunk and I load it into some open page frame. And I can do that without worrying about having any external fragmentation, because this size is equal to this size. They're the same number of words in memory. Okay? And then I'll take this next chunk, okay, and I'll load it into some other location, right? And this may not fill up an entire page, okay, but the leftover space we just leave blank, because we're only moving around chunks of pages, right, of page size. Okay? Does that make sense? Any questions about sort of this high-level theory about what we're doing here? All right, so we need one more component. We need a page table. I'll put this over here. I need a page table. Okay? And each process gets a page table. The page table is a multidimensional array, a matrix, a table, call it what you will, that converts page numbers into page frame numbers. Okay? So from our previous example, this guy has 2 page frames. Okay, so there's 2 entries in his table. P1 goes to PF1, so it's 1 to 1. Lucky. And P2 goes to PF3, so it's 2 to 3. Okay? Like so. 1 to 1, 2 to 3. Okay? So, a logical address for a specific word, okay? And remember, a word is the size of an address, right? It's the amount of memory that gets its own address, right? Does that make sense? The memory is divided up into some number of addresses. There are some number of bits per address, okay? That's a word. I think of it as like the smallest chunk of memory that we're going to be dealing with. A logical address is made up of a page number and a offset, which I'll call W. We're going to use the book's notation here in just a second. Okay. And what what we do is we take, so this whole thing is its address. We take however many bits this is, and it's 1, and we look it up in this table, okay? And we say, oh, look, 0001 is at page frame 00001. And so we go to page frame 0001, and we add to that the offset word, okay, right here, which is the specific address inside that page number, okay, which is some number of bits. And this is how we translate a virtual or logical address into a physical address when we're doing paging. Okay? I can do better than that. Y'all look confused. I have stolen a graphic directly from the book. Okay? All right, so this is all 2 of these. These are 2 different approaches for carving up logical address space into pages, okay? This is the same logical address space. The addresses are, in this simple example, 1, 2, 3, 4, 5 bits long, okay? That's the number of bits we need to represent however many total values we can get in 5 bits, right? This is the number of words in our memory, okay? So what is it, 2 to the 5th minus 1? Right, total number of addresses. Okay, do I need to do a review of binary, or are we comfortable with binary? I need to do a review, or we're comfortable? We're good? Okay. So, address 0, address 1, address 2, address 3, address 4, so forth and so on, right? Just don't worry about P and W right now, just look at the whole number, because that's the entire address for all of those memory addresses. Word size memory addresses, okay? If I take the leftmost 3 bits, okay, then I am dividing up the entire memory space into pages that are 1, 2, 3, 4, 5, 6, 7, 8 words long, okay? So I get the individual word offset in the, rightmost, I think I said leftmost before, I meant rightmost 3 bits, and the page number in the remaining 2 leftmost bits, okay? So if the page is 8 words long, then 00 indicates that this is the 0th page, or the first page. And this is the particular address that we're going to, the particular offset. So if you want 00101, okay, then you're going to page 0, offset 101. It's right here. Okay. Likewise, if you want 11100, okay, then you're going to page 11 and offset 100. It's right here. Okay. Well, that's stupid. Why did we even divide those up? Well, consider that we can, if we make the size of the page smaller. It's not how you want to look at it. We're doing it. We can think of it either way. If we use 2 bits to indicate the size of the page, then the page will only be 4 words long. If we want the page to only be 4 words long, we should just use 2 bits, the last 2 bits in the address, because then 00000 encompasses all 4 of the possible words in that page. And 00001, right, represents all 4 of the possible words in page 1. And 010, right, represents all 4 of the possible words in page 2. Okay? So you've got your address. Okay? You've got your logical address. And let's say it's 10 digits long. I don't know why it would be, but let's say it is. Okay? And I'm not going to draw many of these, obviously. Okay? If we want our page size to be 4 words long, we should use the rightmost 2 bits to be the word, and then the remaining bits to be the page. Okay? Because notice what happens when we get to the next page. Okay? We go back to 00, 000. And then the next one will be this same page number, 001. And then this same page number, 010. And then so forth and so on. Okay? 011. And again, I'm talking about this being the 2 bits that make up the 4 words, okay, in the page. So every 4 words gets us a different page number, right? What happens if we use 3 bits? What happens if we don't do this, but instead we use 3 bits to represent the offset, okay? Then we get to the 3rd, or 8 words, okay, per page. I'm sorry, this should have been, should not be 0000. This should have been, where did I go? What? I put too many things in here. 01, 01, so forth and so on. Okay. And if I wanted to use 4 bits, I could have 16 words to the page. Okay? And I get this falls out for free. That however many bits I apply to the size of the page, the number of words in the page, the remaining bits number the pages for me. Okay? Any questions about that? So that's what we're doing here. Different number of bits to represent a larger or smaller page size. The remaining bits always number the page for me. So if we're taking up 3 bits for offsets, that means we got 1, 2, 3, 4, 5, 6, 7, 8, and the remaining 2 bits tell me what page we're on, either 0001, 10, or 11. Okay? Or 000, 001, 010, 011, 100, 101, 110, or 111. Okay? Now, that's just how to carve up the logical address space. We still need to look at what does this mean when we use a page table. Okay? You build the frames, so that was for pages. You build the page frames in effectively the same size, in the same way. They have to be the same size. Okay? Again, stolen directly from your book. So this, on the left-hand side, is our logical address space divided up into pages that are 4 words long. Okay? We also then need to have our physical address space divided up into frames that are 4 words long. Okay? So we use 2 bits to manage the offset for every frame. We use 2 bits to manage the offset, to address each individual word in every page frame. Every page frame. Okay? So if a logical address is 000xy, it could be xy could be 00, 01, 10, or 11, because x and y are both binary digits. Okay? Then a place where we would look up potentially would be 0001xy. Why? Because 000 is mapped to 0001. In other words, page 0 maps to frame 1. And the specific word that we want to get at is in the same offset from 0 as it is from 1, because they're the same size. Okay? Ask me questions. We're doing it down here too. Page 3011 maps to page frame 1111. What's that? 15? Okay. Or is that 31? Is it what?
4 1 to 15, 5 1 to 31.
Okay.
What is the, and maybe it's a stupid question, but if page 000 maps to F0001, where does the 1 come from? I'm just kind of.
You here? You mean 000 to 0001?
Yeah.
This P is the page number, which remember is the chunk of memory in the logical address space. Okay, it's going to be there's going to be a bunch of page zeros, because effectively every process is going to have page 0, its own page 0, right?
The mapping is highlighted, it's just hard to see on the projector.
Oh, is it? Yeah, let me see. Any better? You see the yellow highlight there?
Yeah.
It's clear in the book, it's clearer in the notes.
Okay.
Okay. What's not shown here, though, and this is a good question, because what's not shown here is the page table, right? Which maps this page number to this frame number, and this page number to this frame number. Okay? So internal to each process, so this is one process, internal to each process, there will be a page table that tells it where all of its pages are, and it will turn these 3-bit numbers into 4-bit numbers, because there are more page frames than there are pages. Okay? But don't let that pacify you into a false sense of security. There's more page frames than there are pages for a single process. But there are not still enough page frames for all the pages for all processes. Right? Does that make sense? Okay. Thank you for that question. Other questions? So, one problem that comes up then, and I hinted at this, I alluded to it earlier. One problem that can come up is we were worried previously about, go back, external fragmentation. Okay? External fragmentation is called external because it's external to each individual process. So imagine you're a process, okay? And you're like, where did all the computer's memory go? Okay, it was due to fragmentation from swapping, okay? Internal fragmentation is now what we get into when we start talking about paging. Because, remember, every process's logical address space has to be divided up into a certain number of fixed size chunks. How likely do you think it is that a process's address space will be an even multiple of that fixed size chunk of data? It's not going to be, right? So you're going to take the first chunk and you're going to fill a whole page. Then maybe you take the next chunk and the next several chunks and you fill pages, okay? But the last chunk is not going to be big enough to fill a whole page, but it's still going to take up a whole page, right? Because we have to move entire page-sized chunks into page frames, right? And so what we're going to end up with is that last page is never going to be big enough, never going to be enough data to fill that last page. And so we're going to have a bunch of page frames that have a bunch of meaningless, empty space in them. Okay? This is internal fragmentation. We lose the ability to use all of our memory, right? Because of that artifact, because we're trying to divide up the load modules into fixed sized chunks. So do we get anything by using paging?
We get to use all the slivers of memory.
Okay. We sort of get to use all the slivers of the memory. Because again, there's still slivers of memory. It's just that those slivers they're allocated to a particular process, but the process doesn't need them, right? So yeah, I mean, we traded memory slivers that were between processes to we just allocated them to processes that didn't need them. That's what internal fragmentation does.
That means your slivers are going to be larger because
Not necessarily. We don't know on average what percentage of that last page processes are going to take up, right? Probably, I would venture a guess that they usually take up about half of the last page, just on average. Many will take up almost all the last page, and some will take up, about the same number will take up almost nothing of the last page. And so the average should come out to somewhere in the middle. No guarantee, though, about if that's a bigger hole or a smaller hole than we had before. But what we do get from using paging is we do not have to worry about managing those holes, right? It's not like the memory is getting fragmented so that we can't use it, because when we get ready to swap pages out, this is called paging, by the way. When we get ready to swap pages out to make room for other pages, we swap entire page frames out. So just like dump this page frame, or write it back out to the module on the disk, and then load another page frame. Okay. So that frees the operating system from having to be like, all right, I need a hole big enough for you. Where do I look? Right? If there's an open page frame, guess what? The hole sizes match. Boom, you're in. Okay? If there's not, then we need to keep track of some method for keeping track of what pages happened most recently. Okay? I have somewhere in the notes we'll come up on, but I'll go ahead and mention this. This notion of what's it called? Oh, it has a official name. It's slipped my mind. It's mentioned in your book, but the notion is that the next instruction is going to be very close to the previous instruction that got executed. Okay, does that make sense? So most of our instructions are going to be grouped together in code chunks, right? You can understand why. Like everything is divided into functions, right? So those functions shouldn't exist if there's only one or two instructions in each function. All right, does that make sense? So the proper function size should be big enough to be meaningful as a function, right? And so most of the time, the next operation will be very close to the previous operation in memory. And so what we usually end up doing is we swap out pages that have been in memory for a long time, right? And if they've been in memory for a long time, then our theory is that maybe like this was a process that finished, and so its calling function is not going to need it anymore. We don't need to keep things. We don't need to keep operations or data that haven't been used recently. So we move those out first, and then we move the new page frame in whenever we have a page fault, right? Which is where I look up an address and it's not in memory yet. Okay. All right. So it's not a perfect solution. We still have to deal with fragmentation, but it's fragmentation internal to each process, so we don't care as much because we're moving whole memory chunks around, right? Every time we load a chunk, a page from some process, we're loading it exactly into the size frame that it needs. Okay. Any questions about that? All right. There is a problem that I haven't talked about yet that comes with paging. I mentioned that you've got in your load module, you have all the things that are going to be stored in memory. So that includes your operations, okay? Say the code itself, okay? That includes your static data. That includes your stack, and that includes your heap, okay? Now, normally, when we think of this as a single load module, okay, it's very common for us to put all the operations out up front, okay? Then the static data together, and then the stack together, and then the heap together, okay? When we divide this load module into pages, what is naturally going to happen? Remember, all the pages are the same size. I'm going to try and do this by hand. Make them look like the same size. So that's one page. Okay. Here's another page. Oh, terrible, terrible. These are meant to be the same size. Okay. Here's the final page. Right? Now look down here. This is the internal fragmentation. That chunk of data is not there, so it's just empty for us. Okay? But notice something else happened. This chunk is going to get stored somewhere in RAM. Let's say it gets stored up here. This chunk is going to get stored down here. Okay? This chunk is going to be stored up here. So the heap stays together in this case, but look, the stack doesn't. This data that's in the stack got arbitrarily split. Okay, got arbitrarily split. And so this chunk went over here and this chunk went over here. What if we split a data structure in half, right? An array or some other user-defined data structure existed in memory, contiguous or at least close to each other inside memory in terms of the load module. Now two pieces that were right next to each other in memory are very far apart now. Okay? The operations are all together, but the static data got split. Okay? So dividing up these components of the code makes executing the code reliably hard. Okay? That's called misalignment. So it makes sharing and the protection of logical components difficult. Okay, so you've got this misalignment that comes in when we do paging. Okay? So how do we get rid of this misalignment? Anybody want to take a stab? When do you see this word? Oh, you guys can't see. Hang on. When do you most often see that word? Yeah, when you have an error. Do you have any idea what that means? So it's usually when you go outside of the memory that you're allowed to access. Yeah, you can have a segmentation fault or a seg fault, as it's often abbreviated. So what is a segment? What is segmentation? All right, so a segment is a variable size block of a logical address space. How's that different from a page? Yeah.
The segment can be non-size.
Yeah, and the page is, yeah, so the page is set, right? All right, so let's get rid of, just for a second, let's get rid of pages. Let's get rid of this notion that we're going to be moving page-sized chunks in and out of RAM, okay? Instead, let's think about moving entire segments in and out of RAM. It's not a whole program. It's not a load module. It's just a variable size chunk of a load module. That'd be great, because what I'd really like to be able to do is I'd like to be able to move all the operations, the instructions, okay, into memory as one chunk. And I'd like to be able to move all the static data into memory as one chunk. Or perhaps operations and static data together into RAM as one chunk, as one segment. And then the stack will be moved in as one segment. And then the heap can be moved in as one segment in by itself. Okay? So in order to facilitate this, we make use of a segment table. Okay. Right. So a logical address is again divided up into two parts. Some number of bits for S and W for a word offset for the nth, the Wth word in the segment. This works just like pages, okay? How big do you want your segments to be is defined by how many bits you use to keep up with the number of words in each segment, just like with pages. Okay? Segment addresses or segmented addresses and paged addresses, the same idea. Okay? Then we have a segment table. And the segment table is as big as the number of segments we have in our process. And S that represents the segment number. So we look up the segment number, okay, as the Sth segment, and we find it right here. Here's segment S. And the segment table has two parts. It has the size of this segment, and it has the segment address, which refers to the address in physical memory where this segment has been loaded. Okay? We then take the W part of the logical address and we add it to SA as the offset, okay? And we read down that many words until we find address SA plus W, and that is where that specific offset in that specific segment is stored in physical memory. Okay? So the table looks very similar, but there's actually an extra wrinkle here. This has one more thing that paging doesn't have. Okay? And the reason why is because if we know that all pages are the same size, then it's very easy to detect if it's easy to detect if W goes past the page, right? The W that you give us, because of the width of a page, must necessarily be inside that page. Okay, so it's not like you can use an address. We're not doing this addition thing where W could go past the size of the segment. Okay, but with segments, there's no predetermined set fixed size of each segment. So what we do is before we let you access segment address plus your W offset, we check to make sure that W is not greater than size. Okay? And if W is greater than size, then what you're trying to do is you're trying to access a segment, you're trying to access past a word that is past the end of the segment you say you're accessing in. Okay? In which case, we give you a segmentation fault, okay, an error, right? This comes up when you are using pointers. It comes up when you're using dynamic allocation. It comes up when you're using indexes, right, to index past the segment, right? Not all the time, but sometimes when you try and index past the size of the array that you've defined, if you go too far out, you actually end up breaking past the end of your segment, in which case you get a segmentation fault. The operating system compiler says, hey, look, or the operating system does. The operating system says, sorry, this is an error. The offset you've given us is bigger than the size of the segment you seem to be trying to access in. Okay? Questions about that? What's bad about this? What's good about this is we get to not have misalignment. Okay? But what's bad about this approach?
Not as organized. The external fragmentation is still a thing.
Okay, external fragmentation is still a thing, right? In fact, we're doing nothing to mitigate external fragmentation. We threw away paging. Paging's whole purpose was to mitigate external fragmentation so that we don't have to worry about it anymore. We, the operating system, don't have to worry about it at all. If we're not doing paging and we're doing segmentation, then yeah, we get to have smaller segments. We get to divide up our object module into smaller segments of varying sizes. But that's not any different than just having like smaller object modules, right? It's just on a smaller scale. And so the external fragmentation is still a problem. As we swap these things in and out as we need them, okay, we're still going to have to find holes that are big enough. We're still going to have to figure out which hole is the quote unquote best to choose from. And we're still going to have ultimately an increasing fragmentation, right, as we move along. Okay? All right. So the question now is, can we have the best of both worlds? Can we do segmentation and paging at the same time? Yes. Yes, we can. Okay? So the logical address space consists of multiple variable size segments, but each segment is divided into fixed sized pages, right? So instead of dividing the whole object module, or load module, I should say, load module into pages, which leaves us with the probability of misalignment, let's divide each individual segment into pages. Okay? It's like pushing this notion of paging one layer down so that we're not paging over the whole load module, we're paging over variable sized components of the load module. And those variable sized components will be broken up according to the components that we want to keep sort of together in memory. All right. So what does that look like? Again, the books descriptions are pretty good, so I've stolen it again. So a logical address this time is divided up into three components: S for segment number, P for page number, and W for word offset. Okay? And we need both a segment table and a page table. Both a segment table and a page table to be able to translate from the logical address into the physical address. Okay? Because it's not just the entire program that's getting divided up into pages, it's each segment is getting divided up into pages. So each segment in the segment table, each segment numbered, go to that number, you see the size of this segment, and you see the page table, PT value, for that segment. Okay? If the total of the page number and the offset is bigger than the size of this segment, then you've got a segmentation fault. Okay? So we'd go over to the page table, right? PT, page table number, and then we look up what P is, right? And we find F as the frame number in physical address, okay? And then we add the W offset to that, just add it directly, down W spaces, because the pages are the same sizes as the frames, okay? Even if the segments are not the same sizes as the page, each segment is divided up into a certain number of pages, right? Then we just offset down by W, and then we found the specific address that we were looking for. So SPW is at location FW in physical memory. Okay? Do segmentation first, then page each segment, and then you can look up, using the page table, where each segmented page, or paged segment, I guess, is in physical memory. Right. Questions about that? See a problem with this? It works, but what? Put on your engineering hats and tell me why this might be a problem. How many times, when do I have to do this translation? When do I have to do this translation? What?
Every time.
Every time what?
Try to access it.
Every time I try to access a memory location, okay, I need to do this translation. That's going to happen quite a lot, right? Every time I try to access memory, I have to do that translation. Happens quite a lot. What do you notice about this translation in comparison to a simpler like this? Right? There's an extra step. Okay? So how much work do each of these translations take? Right? Because in this one, we had an extra, it's not shown here, but the page table, right? To look up this and find this value. Okay, there's an extra page table here. Now we've got effectively two tables that we have to do lookups in before we were able to look up in physical memory, okay, the physical address. So paging and segmentation both double the number of memory accesses required, okay, whenever we're looking up memory. And together, this arrangement altogether triples the number of memory accesses that are required when I look up a memory address. Okay? That's gonna cause a deficit. We're gonna take a hit in performance. Okay? Because two of every three memory lookups is going to be given over to translating from the logical address to the physical address, and only the third of every three is going to be actually useful for our lookup, decode, execute cycle. Okay, the thing we actually want to do. Right? Does that make sense? So this is going to slow us down. It's going to slow us down a noticeable amount. Okay, but what we do like about this is we like that we have handled misalignment. We like that we have handled having to manage holes in memory and external fragmentation. Okay, we don't have misalignment. We don't have external fragmentation. We don't even have to worry about it because we're still moving whole pages from the disk into RAM. Okay, so we like that. Can we have this and still be relatively fast? What will we need? The answer is we need a special place in memory, and it's called the translation look. Too many O's. Get rid of one of those O's. Look aside buffer. Pretty sure look and aside are hyphenated. Okay? The translation look aside buffer. Remember how I said that the principle here is that, this is the principle of locality. That's the term I was trying to think of before. The principle of locality says that addresses that are next going to happen, okay, are going to be close to each other, right? So what I should have, okay, I should have a fast memory register, okay, a register on the CPU itself, even faster than RAM, okay, a register dedicated memory on the CPU, okay, and each time a logical address is translated into a physical address, I'm going to store the SP to F translation, right? I'm going to pair those numbers together in that table. Okay? So if you're looking for SP, I'm going to tell you it's over here in F. Right? That's going to save me doing these two lookups. It's going to turn two lookups back into one lookup. And it's not a memory lookup, right? It's actually a cache lookup, which is even faster than RAM. Okay? Now, why don't we just do that all the time? Why don't we just store all SPs in cache memory so that we have a giant table for the whole system where every SP looks to an F? Cache is expensive. Cache is limited. It's small, okay? Because it's expensive, right? It exists on the chip. Sure, you could theoretically make a chip with enough transistors that it could store the entire computer on it, right? But it would be astronomically expensive and limited to that specific computer and architecture that you had in mind. Okay? So that's why we don't do that. So the net result is if we use a translation look-aside buffer, okay, then we're going to run out of room in that buffer, in that cache memory, eventually. Eventually, you're going to ask me for an SP combination, and I'm going to look it up in the translation look-aside buffer, and it's not going to be there. In which case, I then have to look up the segment table, and then I have to look up the page table, and then I can look up physical memory. But before I access physical memory, I need to put your new SP and F combination into that buffer, which means I need to remove or overwrite some other SP and F combination that was in the buffer. Which one should I overwrite? I'll go ahead and tell you why. Because I believe in the principle of locality. So which one should I override? Do what? Not the one that's farthest away. I don't have a concept of far away. What do you mean by far away? So it's the locality we're talking about is not the memory in the RAM, but the memory in the logical address space. Right? Does that make sense? You're on the right track, though. You're very much on the right track. I don't know. I see what you're saying. It's not quite the answer I'm looking for. I don't have the lookup that you're looking for. I need to put it in the table, which means I need to replace one. So which one should I replace? You say, you should replace something that is far away, a very far away part of memory. But I don't know that just by looking at SP and F, right? I don't know where these SPF combinations are. I don't know which SPF goes with which process. I don't know how close they are in logical memory. Yes, sir, in the back.
Least recently used.
Okay, so some algorithm similar to least recently used. Okay, if I haven't looked it up in a long time, then it's likely that I'm not executing in the memory that that is required by this translation to get to. Okay, So like if I haven't accessed this record in the table for a long time, then I'm probably not gonna access it anytime soon. Okay, so I'm gonna replace that. Is that a perfect solution? No, of course not. Not a perfect solution. But the principle of locality does seem to support that solution. All right, any questions? So I have not graded your exercise number 5s yet. It's on my next to grade to do thing. There will be another exercise coming out. I really don't know what it is. I haven't started building it yet, but that's also on my to-do list. Give you guys another exercise. This is the end. This lecture today finishes out our memory management. The schedule originally intended for us to do that in one lecture, but I just couldn't do it. It takes 2 lectures to do. So next we'll be moving on to chapter 7, which is more specifically talking about virtual memory. Okay. All of this, in my argument is all of this is really virtual memory, but what we've been building up to is what you would officially call virtualized memory. Okay? All right, I'm done. I'll see you guys next week.